One of the fundamental components of any fluid power system, of course, is the pump. The pump is what takes the rotational mechanical energy, as I mentioned before, and turns it into the fluid energy. So it's the core. Almost every hydraulic or fluid power system is going to have a pump that is going to create this flow. So we're going to spend some time looking at pumps. We're going to look at some different types of pumps and how they operate. We're going to look in detail at some efficiencies and where those efficiencies play and how that will affect how we design fluid power systems, how we choose the size of pump that we want to use, because we can get power from one place to another at a high flow and a low pressure, or a low flow and a high pressure, or somewhere in between. So what's the best choice? And so we will look at some of those things, look at some of those efficiencies, and then we'll do some examples where we'll talk about performance of these systems and sizing. All right, so let's look at some different types, and we're going to talk about a number of different things here. But first of all, basic of any type of a pump is the difference between a positive displacement pump and a non-positive displacement pump. Almost everything we do in fluid power is a positive displacement pump. Non-positive is like your centrifugal pumps, and you've probably looked at these in some other courses, or if you haven't had those courses yet, you probably will, where you look at centrifugal pumps. The speed of the pump, how fast it goes, is going to determine how much head it generates, and so forth. So we are not, again, most of the fluid power systems, and certainly at the level that we're going to be looking at it, we're going to stay exclusively to positive displacement pumps. And a positive displacement pump, like that animation you see on the bottom there, means that for every rotation of that pump, of the shaft on that pump, I'm going to get a certain amount of material out of it. Now, there's going to be some variation there with inefficiencies and leakage and stuff like that, but in a theoretical basis, theoretically, that pump is sealed, so like on that piston there, every time that shaft rotates, I pull a certain amount of material into that piston and I push it right back out. And so I get that same volume of material every rotation of that crankshaft. I'm not going to see that with that centrifugal pump over there, or fans or stuff like that. They're not sealed, so it relies on the momentum, the centripetal forces and so forth of those impellers to make it happen. But we're going to be positive displacement. It means every rotation I've got a certain amount of material that comes out of it. Okay? Now, we have to be thinking about that, because then the philosophy becomes, and I'm going to come over this over and over again, I want you guys to really grasp this. Pumps create flow. Pumps do not create pressure. They create flow. So if I have a pressure in a system, that pressure comes from whatever's downstream of that pump that's resisting that flow. That's what's going to increase the pressure. So all the pump is doing is sitting there creating flow. It's pushing fluid through it at a certain rate, depending on how fast we spin the shaft and how big it is. That's how much flow is going to come out of it. That also means then that somehow we have to provide some protection for that pump, because if there's no place for that oil to go, I have close all my valves downstream, for instance, and there's no place for that oil to go, that pump is still going to keep working, still going to keep pushing that flow, and something's going to give. So if I don't have a way for that place for that oil to go, or a way to provide some unloading of that pump, it's going to break something. And I've seen lines blow, I've seen pumps actually come apart. I've seen the case of pumps split when systems were designed incorrectly, or something went wrong, that the relief valve didn't provide the protection for the system. So it actually physically broke the cast iron case on a pump. So they will break things because there's got to be a place for that oil to go. So that's a positive displacement pump. Almost everything we work with is a positive displacement pump. The other thing to think about is this a fixed displacement pump or a variable displacement? And the difference is, a fixed displacement pump, it's the simplest, it's built simply. Every rotation of that shaft, I get a certain amount of fluid out of it. Well, some pumps have some adjustability built into them so that I can change the amount of oil that comes out of it. And I'll show you some different examples of this, where I can say, all right, I want a little less flow out of the thing. I don't want to slow down the shaft because it's connected to an electric motor and I can't really change the speed of the electric motor easily. So I'm just going to change how much oil comes out of it. I'm going to change its displacement, or the size of the motor. And so that's what we can do. So that would be a variable displacement motor. So one that I can vary the displacement of it. Okay, and there's a number of fundamental different types that we can look at there. We can look at a gear and a vane and a piston. We'll look at each one of those, but I want to show you before we go there, I want to go to the slide here and show you what the JIC symbols look like for these pumps. And there's a lot of variations that we can build into these symbols. So if we can zoom into the slide, the JIC symbol for a pump, and you saw it earlier on that earlier drawing, it's a circle with an arrow coming out of it. So again, it kind of shows you, a lot of these pumps are circular like that. There's an arrow coming out of it. And the drawing could be as simple as that. Sometimes we will add a shaft on it to show the rotation. So we'll put an arrow, a circular arrow around that, arc arrow that shows that that's the mechanical shaft that's providing the rotational power. And there's a lot of variation to these, and I'll show you these as we go through, but this would be a pump that's pushing fluid out of it. If I draw another symbol, and I'll talk about this because we're actually going to do two things together. If I have another circle, but I'm going to have the arrow pointing into it. So the arrow pointing in. So this is a hydraulic motor. So this one over here is a pump with oil coming out, and this is a hydraulic motor with oil coming in. And I actually drew two arrows on it, and that indicates that that's a bidirectional motor, so I can go either way. So I can push oil from the bottom into the thing, and that's going to make the shaft, output shaft here, rotate. I can push oil in from the top, and it's going to rotate in the opposite direction. All right, now we'll see as we go through that the mechanisms of motors and pumps are basically the same. So the design is a little bit different in terms of the porting, how the oil gets in and out of them to make them more efficient as a motor or as a pump. But basically, most of these things, in theory and principle anyways, can be turned around and run in the opposite direction. So I can push oil into a pump and it'll make the shaft turn, okay? So that happens a lot. So that's the difference between a pump and a motor. Now, we also talked up here about the fixed displacement versus a variable displacement motor. Now, one of the things we'll learn with JIC symbols is that if I put a diagonal arrow across a symbol, that means that generally indicates that that is a variable whatever. So in this particular case, this is a variable displacement pump. So I can change the size of the pump. All right, and again, I'll show you how we can do that, but I can change how much material, how much fluid is going to move out of that per revolution of the shaft. Okay, so there's just some options, and I'll show you a few more as we look at some different symbols here and look at some different type pumps and so forth. So that's the basics of it, the basics of a pump symbol, what they look like, and that's what we got. So let's look at some different types. So the gear pumps are some of the simplest, and the fact the cheapest pump you can buy is that external gear pump that you see on the left there. And you can see how the material flows through that. There's two gears that run together. They mesh in the middle tightly, and a lot of times we think, okay, it's grabbing the material and pulling the material between the gears and pulling them down as we're looking at that drawing, but that's not true. If you look at the bubbles in that liquid and how they're moving, they're actually coming into that gear pump, moving around the outside. So the material moves around the outside. As those gears come together, they mesh, they squeeze the oil away from the middle of those two gears or the fluid, and then it pushes the fluid on out the top. So we call that a lot of times an external gear pump because the fluid moves around the outside of the gears. And we could look at the displacement of this pump pretty easily. If we could measure the volume of the volume between the teeth on those gears as they rotate, and if we had the depth, going into the screen, how deep that material was, we would know how much volume is in each one of those teeth, and we know how many teeth are on a gear, and we double that because there's two gears, material flowing around the outside of both those gears, and we could determine the theoretical, at least, capacity of that pump, the theoretical flow rate. So that's an external gear pump, again, one of the cheapest. You see a picture of one up above there. They're somewhat unique in their appearance because they're generally an oblong shape, and the shaft comes into one of the two gears. So you can see that the shaft does not come into the center of that oblong, but it comes into one of the lobes on the side of it. And so you can look at that shape and say right off, hey, that's an external gear pump. Again, they're usually the least expensive, but you can start to see now if we think about inefficiencies on these things, where's my inefficiencies going to come? Well, You know, how tight is that seal between the gear teeth and that outside housing? The tighter I make it, the more friction I'm going to have, the harder it's going to be to turn that motor, so I don't want to do that. The looser I make them, the wider the tolerance between in that space, the more chance I'm going to have for material fluid to leak around the outside. So I'm going to get some leakage flow back through. And so we can start to see pretty easily that, hey, we're going to have some inefficiencies there. We could have some inefficiencies. The ones on the right there are really fascinating to look at, and those animations are really cool, but this is called an internal gear pump, and we sometimes call them a gerotor pump, G-E-R-O-T-O-R. But you can see there that there's a gear that has a certain number of teeth on it. In this particular example, on the inside it has 4 teeth, and then there's an internal gear that it meshes inside of that has 1 tooth more. And as it rotates around, you can see the space. There's a space between the inside gear and the outside gear that gets larger. So as that space gets larger, it's going to pull material into it, and then as it continues on around the revolution, it gets smaller and it's going to push the material out. So you can see in the animation on the bottom there how we're pulling material in, and as that space gets bigger, and then as the space gets smaller, we're pushing it back out. Again, this could be operated as a pump or a motor, both of these. So I could turn the shaft and have it create fluid flow, or I could shove the fluid into it, and that's going to make the shaft rotate. So we could do both directions. And I think that animation on the lower right kind of shows that. It shows that high pressure fluid red coming in there that's making that thing rotate. The lower pressure fluid then gets pushed out of the other side. So we can run these either as pumps or motors. They'll go in both directions. So that's a gear pump. Some of the simplest, the most inexpensive type pumps. Let's look at the next pump is a vane pump. And the vane pumps, somewhat similar, but we have a sliding vane. So you can see there's an offset there. You have a disc inside that is offset from the round housing. Inside that disc then there are slots and there's vanes, so just kind of flat plates, if you will, picture flat plates that can slide in and out on that disc. And so as that inside hub or that inside disc rotates, those vanes will move out, and you can see again the space between the inside hub and the outside housing as we move around the bottom of that animation on the or either one of those animations. It gets larger as we move around the bottom, so that's going to mean it's going to take fluid in, pull fluid in, and then when it gets to its maximum and starts up around the top, that space is going to get smaller, so it's actually going to squeeze the material out. So it's kind of the same principle as a piston pump where it pulls it in, pushes it out, but we're doing it more continuously as it rotates. Okay, so those are vane pumps, and again, these can be used somewhat as motors, but not as common because there's often we rely on centripetal force to keep those vanes out against the outside housing, so that they're sealed out there. So that they're going to have a minimum rotational speed, and if I try to push fluid into them, I can actually push the vanes into the disc and break the seal there. So it's a little bit more complicated in terms of how they operate and their operating parameters, what are minimum speeds and so forth. That's a vane pump there. And you got a couple more links there if these are fascinating to you or still having trouble understanding them. There's a couple links there, and I have them on all these slides that you can see some more animations online, some pretty neat stuff that people have showed how these different mechanisms works. So that's a vane pump, and there's a number of different kinds of piston pumps. And in that first slide we showed a very simple piston pump, the piston moving in and out. And these are axial piston pumps, and you can see that one rotating on the lower left there. And you kind of picture this as an old 6-shooter, you know, Wild West handgun with bullets going around this barrel. So it's a barrel. You're looking at a two-dimensional. You can kind of see it in the drawing on the right there where we have that barrel. And as that barrel rotates, we have this plate, this slanted plate on the left-hand side. We call that plate a swash plate. And the swash plate actually is going to be connected in some way. We can do it a lot of different ways, but it's connected to the pistons. The pistons are in that barrel. So as the barrel rotates, you can see that the pistons up at the top are all the way to the left. And so if the fluid is to the right of those pistons, it has drawn fluid in as it's coming up around from the back side as we're looking at the animation. And then as it rotates down the front, it's going to push the fluid back out. So fluid comes in on the back side, out on the front side. The pistons are moving in and out. So if you just kind of follow one piston as it moves around, you can see that it moves in and out. And that's an axial piston pump. You can see in the center there we can have a bent axle pump, or we can just have the shaft, the rotating angle is fixed. And so these are kind of distinctive, odd looking pumps. You can see them. But a lot of them are in line, like you see on the right there, and you can see the bearings and so forth and the cutaway on the front. Now, here's the interesting thing about these axial piston pumps. We talked about these being the possibility of having a variable displacement pump. And I can do that by changing the angle of that swash plate. So if I look at the swash plate, and I'll draw it in here, you can see on the left-hand side that swash plate is at an angle. If I made that swash plate vertical, so if I pulled it up so that it was vertical, then I would have no motion of those pistons. They wouldn't move in and out. So as they rotate around coming up from the back, down on the front, they would not go in and out. So that would essentially eliminate the amount of flow coming out of it. So I can change the displacement of that pump just by changing the axis of that swash plate. And what that allows me to do then is change the speed of things. So this is the kind of mechanism you would see, for instance, on lawn mowers. So lawn mowers that have hydrostatic drive, riding mowers where you just push the pedal, and the further you push the pedal, the faster it goes. My engine stays at a constant speed, but the speed of the mower goes. In the same way, the ZTR mowers that have the handles on them, and we make one wheel go forward and backwards, or both of them go forward, that's what we're doing. That handle is connected to the swash plate on an axial piston pump most of the time. And so when we want to go faster, we tilt the swash plate, we get more displacement out of the pump and the motor, or both. We actually do both of them together for efficiency reasons, and that's going to increase the speed, make me go faster. I bring the swash plates up vertical, I slow down and stop. And so that's how we can change the speed of things, change the displacement. We're essentially changing the displacement, so that would be a variable displacement pump. So axial piston pumps, these are pretty common, especially again in places where I might need to change the speed of what's going on there, of the rotational speed. The other kind of pump that is fairly common to us are radial pistons. And so these kind of put you in mind of an old airplane engine with the pistons going out in a radial direction with a propeller on the front of it. But it's the same concept here. We have a rotating shaft in the middle. And the one on the left is pretty common on a lot of agricultural tractors. Now we can do a unique thing with this. You can see there's an offset cam that rotates in the center of that shaft in there. And that cam, as it rotates, the lobe, as a lobe comes around, it pushes these pistons out. So you can see the pistons here, and they show alternating large pistons and small pistons. We can do it a lot of different ways, but you can see the pistons moving in and out. So they're gonna, as the piston goes out, it's gonna push oil out. As it comes back in, a spring pressure will bring it back in. It'll allow the fluid to come back in. So the fluid comes in and then goes out, in and out, every time that shaft rotates. We can have multiple pistons around these radial piston pumps. Now, the interesting thing we can do with these is to port, somehow we're going to port the output pressure, so the flow that's coming out of this thing, we're going to port it or bring it back into the inside chamber here. Now, why are we going to do that? Well, a couple reasons. This is a rotating part. It's a cam that's sliding on the bottom of these pistons and everything, so I need to provide some lubrication there so they don't wear out and so forth. But if I have that output ported, the input here, if the downstream pressure gets really, really high, that's going to make the inside go to high pressure. And eventually the pressure will get high enough that it'll start pushing out on these pistons. It'll essentially hold the pistons out, lift them off of this camshaft, and the piston stays out and doesn't move in and out. Fluid through it. So the pump will essentially de-stroke itself. We talk about a pump de-stroking. The de-stroking is a pressure compensation. We also use the term pressure compensation. So pressure compensated pump, or pressure compensation. On the JIC, so one way we can do that is look at our pump. There's the output of the pump, and what we'll that is sometimes indicative of that being a pressure compensated pump. Then often we will show pump like this. And so what that's telling me, a dotted line, when I see a dotted line in a fluid power, and pressure sensing means that it's really small, it doesn't carry a lot of flow, its only purpose on the side of that pump knows what the pressure is on the outlet of the pump. And so we can kind of see graphically here that we're pump down here to do something, and that will, in this particular case, like the radial piston pump, it'll tell it to de-stroke and say, hey, break anything, so quit sending oil down there. Don't keep pumping it because it's got no place to go. And so on more modern drawings and some more modern JIC standards, we'll show a pump like this, arrow inside the pump. And again, this vertical arrow, small vertical arrow, we'll see that types of mechanisms, hydraulic mechanisms, and that indicates that it act differently depending on what the pressure is on the system somewhere. So a couple pumps that will de-stroke themselves, and these are the basic mechanisms. A lot of time looking at the subtle differences in the design on these, but that's beyond look at or spend time on. So what we want to focus on is relationships. So how do these work, or what are some numbers? Let's put some numbers on how they're working. So here's the fundamental relationships, and you can see about those on the upper left. We've talked about the fluid power, which is the flow times the pressure. That's a relationship of how we calculate fluid power. And then we have the mechanical power, and we've already dealt with the mechanical power with engines and the engine curves and all that kind of stuff, and that's just torque times speed. So that's how we calculate these things. And so that gives us those fundamental basic relationships of how we calculate power. Now there's some V stands for the volumetric. V is a volumetric efficiency. The volumetric efficiency is really affected by the leakage inside the pumps. So we looked at, like the gear pump, for instance, how the fact that depending on the tolerance between the outside of those gear tips and the housing, there might be some fluid be able to leak back around that pump. And so leaking efficiency. The next one there is a subscript T, and that stands for the torque efficiency. You'll also see some textbooks use an M for mechanical efficiency, but to indicate the same things. But basically, this torque efficiency is affected by the friction. So there are bearings in these things that we've got fluid that we're using is also going to affect that. So it's going to take a little bit of torque to turn these things just to get them moving, and so there's going to be some loss there in the friction. And so the leakage and the friction efficiencies both go into the power efficiency. So the third one down there is the power efficiency, A to sub P, and while that oftentimes when we do these calculations, we're going to use one number for the volumetric efficiency or the torque efficiency or power efficiency, but we're going to see that these vary a lot, and there's a lot of different a couple different factors that will make these frictions components vary, and that's going to flow, we can get the same amount of power both ways. What's the most efficient way to do that? So we'll see some things that affect these efficiencies. But let's move over to the other equations over there. You see I have two sets of identical equations. And I've laid these out because we're going to have to look at pumps and motors separately when we consider the a pump is going to be the fluid power I get out. Likewise with a motor, whatever fluid power I put in should equal the mechanical power that I get out. Okay, now keep in mind, let me put the symbols down here. We have to think about and be careful about what is our input and what is our output. So here's a pump symbol, and there's the mechanical shaft going into it. So the input to a pump and we know there is, which is going to be bigger? Well, it's going to take more input to get less output out of it, so that fluid power is going to be smaller than the mechanical power. So let's look up at the equation up above there. Theoretically, they're equal. In actuality, they're not. The mechanical power has got to be a little bit bigger. I've got to have more mechanical power to be able to produce a certain amount of fluid power. So what I need to do is divide that by the power efficiency. So I'm going to put the power efficiency in the denominator. I divide by a number that's less than 1. These efficiency numbers are all a fraction of 1. I divide by a number that's less than 1. That makes that overall a bigger number, and it matches that mechanical energy. It shows that the mechanical power is a little bit bigger. Okay? Likewise, let's go through much material, how much fluid is going to be displaced or moved through that pump in one revolution of the shaft. So units are typically cubic centimeters per revolution or cubic inches per revolution, something like that. Okay, so that's the displacement of that pump. So how much would we move through? So if we look at this, the right-hand side of the equation is the theoretical. So the displacement times the rotational out than what I should. So to make the left-hand side of the equation smaller, I'm going to multiply this now by the volumetric efficiency. Because of the leakage and stuff like that, I'm not getting as much out as I theoretically should. So the volumetric efficiency multiplies in that equation. Torque equation, same kind of thing, all right? Torque should be. So we can follow through the units. We'll do some examples where we do that. So that's the theoretical torque. All right, can I get that much? The torque, now what is the input? We have to ask ourselves, what is the input? The input here is the left-hand side of the equation. The torque is what I put in. That's the mechanical part that's coming into the displacement. So which one should be bigger? Well, the torque has to be bigger. So this, again, I'm going to have to put in the denominator just like I did with the power up above there. So I put the torque efficiency there. So there's the relationships for a pump. All right, so divide in the first equation, multiply in the second, divide in the third equation. Circle with the arrow coming in. So I'm pushing fluid power into the thing. What is the input? The input in this case is the fluid power. The output then is the mechanical power. So that is the output. So everything is going to be just exactly opposite for a motor. Power to get a certain amount of mechanical power out of it. So these equations are going to be exactly opposite. So in the power equation, I'm going to multiply by the power efficiency. And the flow rate equation, I'm going to divide because it's going to take more flow rate to get a certain multiplied by the torque efficiency or that friction efficiency, and that tells me that I'm not getting quite as much torque out of this thing as I theoretically should. So those are the relationships. We're going to take a few minutes now and the slide here in just a minute. Keep these equations. We're going to go through some examples of how you calculate these. We specify motor and so forth. Go from there.